So welcome back, everyone. Let's see if this you want to use the microphone? Good. So welcome back, everyone. This works. 1, 2, 1, 2. So we're ready to start our last stretch for the day. Don't forget, dinner is on us. You're all invited, but you have to show up at the lobby at 6:45. Right? 6:45. So the bus should leave around 7. Okay. We should have 2 dishes, one fish, some entrees. I like the place and I like the food. So I hope you enjoy it.
Royal Orchid Lobby.
Orchid Lobby, not Rockamart Lobby. Orchid Lobby. Okay, it's just outside where we have food every day. Okay. So please come.
We'll be back a little bit later than the schedule says.
Yeah, most probably. Yeah. We will go with time, so the restaurant should not be full, so they will have a reservation for all of us.
Talk about the picture.
The group picture. Good, thanks, Pedro. After this session, we all go out for a group picture, okay? That will pay us for dinner, okay? Group picture is very important.
You're going to check it on the bus if you're not in that picture, right?
Yeah, you cannot go. Yeah, that's right. So for this afternoon session, we have this first talk, a multi-scale ensemble-based framework for predicting compound coastal riverine flooding with Fares from Stevens Institute of Technology. Thank you for coming.
Thank you.
You want to...
Oh, I'm good. If you don't hear me, let me know. So, thanks for having me, Roy. Thanks for everyone who organized this workshop. I've really enjoyed the talks. As Roy mentioned, I'm coming from Stevens Institute of Technology, which is located in Hoboken, New Jersey. So this is our campus. And when I acknowledge some of my co-authors, have the privilege of working with Julie. And that's a huge benefit when it comes to modeling and work. So she's been sort of leading part of this effort in advancing the science. And if you're not aware, with Hoboken, that's where Frank Sinatra was born. So it's a very famous place. And when we have visitors in our campus, they ask us, where's your lab? We have a wave maker, but our main lab, we tell them, is this, the Hudson River. This is where we have all our instruments, all our models, and this is where we mainly work. I'll be talking about a multi-scale ensemble-based framework, which is focused on forecasting coastal and riverine flooding. I want to start with this slide, which we all know, but I decided to put this slide because this is the objective of sort of this workshop, and this is what a common objective that we share, which is basically trying to better understand and predict all these processes in the hydro system, right? Which are complex. We saw some of the talks showing the importance of groundwater or groundwater and exfiltration and infiltration. We saw some of the talks that show the importance of soil moisture, rainfall, and freshwater inputs. So very interesting talks, and I'm sure we'll see more and more interesting talks today and tomorrow. In operational forecasting, it becomes also more challenging, as you know, because this is the ideal hydro system, water or hydrologic cycle. But in real life conditions or real-time operational forecast, it becomes more complex because you have different stressors. I'll show you some stressors that we face in the United States. This is just an example of how the annual total precipitation has changed 1991-2012 compared to 1960. And you see increase in rainfall in certain areas of the US by more than 15%. And another example, to give you an example also what happened in Texas, Harvey, with Hurricane Harvey, the National Weather Service, they had to change their legend of total accumulated rainfall. And that's a clear example of how this whole system is changing. Another important stressor is sea level rise, right? So you see areas that are in red that had more than 8 inches of sea level rise for this period, 1960 to 2015. Other stressors is the growing population, right? We see the gradient in the colors. In areas where we are here, you have a gradient that can change from a few hundred people in a square mile to more than 70,000 people in 1 square mile. You see the gradients, and combine that with the sea level rise, so it becomes a huge issue, which leads to increase in imperviousness, right? Let me zoom into some of the areas here. This is New York City, Long Island, and parts of New Jersey, where you see the imperviousness is huge, which is what we showed, the importance of that on runoff. So all these stressors are acting on our system, and there's one more stressor, and there's a lot, but these are just examples, is our aging infrastructure, which is mainly designed on climate stationarity, right? Here you see these dots represent the dams in the United States, talking about more than 80,000 dams in the United States, and the color variation of the symbology is about the age of the dam. So you see some of these dams are more than 150 years old. We also have an example now with Irma where it triggered a partial dam breach in Puerto Rico. I'm not showing the other dams in the world, but a living example is also what's happening now in Puerto Rico, where you had a Hurricane Irma rainfall, and then you sort of created a tipping point or a domino effect on your infrastructure, and now you have more than 70,000 people evacuated there as we speak. So all these stressors are acting on our system, but there's always good news, which is basically at the same time we are advancing, right? We are advancing in computational power. So I like this figure because this is a 5 megabyte IBM hard drive in 1956. Compared to what we have now, where we can run models on, this is like just taking one selfie, is that 2,000 pound, right? And now we have computational power resources. We saw what we're doing with, or what NCAR is doing with WHYDE and other researchers that was not possible to do maybe a few years ago. So running models on the cloud, and also even at the scale of schools or institutions. This is our cluster that we procured at Stevens 3 years ago. It's 1,300 core supercomputer, and this is where we're running all our models on. And this is the project, this was financed by a project we got with Port Authority of New York and New Jersey. They are in charge of all the airports, tunnels, and World Trade Center as well. So this is a very unique project that we have with them, and they are our main client. So what are we doing? We're leveraging the computational power, we're leveraging the advancements in models, we're leveraging the data in order to better forecast compound flooding, better forecast hydrological flooding, and better forecast coastal flooding. And one of the things, or the science questions we're trying to ask at the same time, is we're trying to evaluate how the weather or meteorological inputs propagate through these models and translate to uncertainty in the forecasts we provide to our sponsors. So I will show you an example on the Hudson River basin, which is what we see here. Okay, and it has drainage area of approximately 36 square kilometers. Average discharge is 620 cubic meters per second. And I'll show you some unique case studies that we're doing there. And I'll show you also some zoom on a local scale or hyper resolution area of interest. What happened? Why is this very challenging to model? We've been noticing more and more of extreme rainfall events, coastal storm surge, and so on. For example, what you see here is the total accumulation of rainfall during approximately less than 24 hours. Hurricane Irene 2011. Some areas got between 250 and 400 millimeters over that 24 hours. So what happened here? This is an observed water level, okay? And this is in Albany. So the Hudson is tidal. You have freshwater inputs coming from different contributing or drainage areas. And here, as you see this peak in that gauge station from USG, as you see the storm surge from Irene. But at the same time, you had the time of concentration or drainage coming from these different subcatchments. And now what you see basically is this is freshwater input, but that gauge is still recording water levels, right? And what you see here is from freshwater, but the gauge doesn't know that, right? It's just recording water level. And this basically pushed freshwater all the way to the outlet of the Hudson, which was one of the first times we witnessed that. So a lot of complexities in modeling this system. So in order for us to represent such systems, we had to come up with a multi-scale ensemble-based framework. So what basically we do is we take different components. We take regional, global and regional weather models, inputs from these models. We have our own models that are implemented on the Hudson River Basin, which I will show you. We have a regional ocean model and a intermediate ocean model, which is called the New York Harbor Observing and Prediction System. So that's the coastal model. It's a special configuration of the POMS, Princeton Ocean Model. And this coastal model basically goes from 7.5 kilometers at grid resolution to less than 50 meters in the New York, New Jersey harbor area. So we're taking these different components, multi-scale, until we can reach this level of complexity. And if you see this here, you start seeing an area on the Passaic River where basically you have storm surge coming in, freshwater inputs, and you start seeing how the interactions happen between these two different components. So it's very important to have them sort of connected. This telescoping capability that we have runs on the Stevens supercomputer, which I showed. And we're providing forecasts from 72 to 96 hours out. And all our forecasts are forced with ensembles. We're forcing them with more than 100 ensemble members from GEFS, ECMWF, CNC, the Canadian model, from SREF, and we have also deterministic members. And we're trying to come up with envelopes of uncertainty that we can show. This is just a classic model setup of how we implemented the HMS model, which is the US Army Corps of Engineers model. It's a semi-distributed hydrologic model, so it's not like WHYDE. WHYDE, you get more details within one subcatchment or drainage area. Here you sort of have a lumped or lumped methodology, but we're forcing it with gridded precipitation. We're forcing it with reservoir data and so on. And we were successful in running this on Linux, which was sort of a huge challenge because most of these models run on Windows and they're not designed to run on Linux and operational mode. These are just some hydrographs. So we calibrated and validated for Hurricane Irene. This is some of the peaks that you see. Our NASH is very high here, as you can see. So it's a sort of a well-tuned model. We use the Monte Carlo optimization methodologies in order to get such results. And what we're trying to see is basically if I use such model and with a retrospective forecast from an ensemble, what will I get? Which is what will you see here. What do we see? We see that these ensemble members have spread. So there's a huge spread in the precipitation. And we want to see how that propagates in the model, right? So what you see here is the accumulated rainfall. It's just an example of one given event. This is not Irene. But you see, you have a model that's telling you that basically you'll have less than 1 inch of rainfall compared to a model that's telling you you'll get more than 2 inches. So it's the hydrologic model itself, regardless of how much you tune it and how much optimization you do on the parameters, at the end of the day, it's going to have this as an input, which will propagate in the model. So how does this work? Basically, we tested 3 different retrospective forecasts. We took Irene, and we took rainfall data retrospectively from GEFS 21 ensemble members, and we started looking at the spread in our hydrological forecast. This is for one given station, and you see here the spread is sort of high 3 days before the event. And then as we approach this event by 48 hours, we start to see that even ensemble members are sort of all coming together, the wisdom of the crowd, basically saying there's something that's going to happen, right? And then as we approach this event by a few hours, it's sort of definite that this is going to happen. We combine these forecasts with what we call a threshold exceedance diagram. So what you see here is 3 forecasts issued at three, like this one is 72 hours before the event. And at this point, the spread is telling us that there's a possibility of 50 or 60% of my ensemble members are telling me something is going to happen. But as we approach the event, we're sort of certain that this is going to happen. Okay, so this is work that we published in HES. This is also another plot that's showing us the uncertainty in the coastal part. Okay. But before that, I want to show this. Anyhow, this is not working, but basically, we are showing the skill of more than 100 ensemble members for just one given station. And what you see here is Hurricane Irene last year, and it's showing us basically that how the uncertainties from these different global models are varying. The black is what was observed in Irene, and our models are forced with the inputs from these models, right? And this propagates to the uncertainty that you see here. Although, when you look at it, we sort of, the median of all these ensemble members is showing us some sort of a good skill when you compare it to the observations, and this is the Nash. So some of the ensemble members are really producing some good results, and my average is sort of here, so which is still representative in a forecast. But again, regardless of how much effort we put in optimizing these parameters, it's always the spread in the rainfall that is sort of creating that larger envelope of uncertainty. What you see here is the uncertainty in the coastal model, right? So here, this is the spread in storm surge, the gray, the smoke we call it. And again, this is a forecast that we have 3 days in advance, and it's showing that some of these results are representative in terms of predicting this event. All this data goes to the Stevens Flood Advisory System. So it's a website we have, and you can click on these different coastal hydrological stations. You see the color changes based on if there's a flood or not, so that color changes, and then you can get time series. But that's not enough for our clients, because they really like the time series, but they are facility managers on the ground. You have New Jersey Transit that wants to see if they have to move trains or keep them. So they want something more quantitative to give. What you see here is basically their facilities that we forecast. This is the Hackensack-Passaic area that I will talk about specifically. Here you have Newark Airport. Vincent, I know very well the airport. We spent some time there because our flight got delayed. JFK, so all these facilities, they really like the time series that we're providing, but they really want to say it, they want to look at critical infrastructure that they have inside that facility, which means we have to go into really hyperscale models. These are some of the sensors we installed there. So we installed dual sensors. So I'll show you this part, which is a critical area because you have reservoirs in the upstream, you have tide gates, you have wetlands, you have backflow conditions, and it's sort of, you see in that interface between the coastal and the hydrologic component. It's very important because it's highly urbanized, so flooding is a big issue there. You have a reservoir that has, it's not a huge reservoir, but it's still created issues downstream, I'll show you. And this area was mainly wetlands, but the wetlands has been substantially reduced to build on it. You have here Teterboro Airport, you have the NJ Transit, here you have Newark Airport, and so on. So what do we see here? August 2011, I spoke about Irene. Not enough time for the operational people. They didn't get a good forecast. They didn't release the water on time. And that reservoir starts to overtop water, which is why you see this peak downstream registered. This is the rainfall accumulation. And then you have a storm surge at the same time. 5 minutes? 5 minutes? Oh, I thought you said 5 minutes. No, you're in charge. I'm okay, good. I thought you said 5 minutes. I said, where did the time go?
I'm sorry.
Anyway, so again, you see the complexities, storm surge, accumulated rainfall here in Newark Airport, and this is the extent of the flooding we got. That's 2011. 2012, it's a completely different story. Sandy came, Hurricane Sandy, we heard about that. And what happened here, basically, if you look at that gauge station I showed you, you have a measured peak in the water level, but you have no discharge. And this is basically because this is a USGS gauge station that measures water level. So the gauge doesn't know if it's coming from upland or from coastal. It's still going to give you this peak. But you cannot convert it today with the rating curve to get a discharge, right? So that's why this is missing in USGS, because this water here is from surge. Surge propagated all the way to the dam. Fortunately, there was not an issue of rainfall at that event with Sandy. We had less than 50 millimeters of rainfall, so you didn't see that effect from overtopping or upland hydrology. It was mainly surge, but this can happen. And this is something we are actively working on, which is an event that we want to call Sandrine. So Sandy with Irene, we'll see what happens. This is the surge from Sandy, and this is the inundation. So we simulated this. We forced our models, 2D hydrodynamic models with high resolution grids. We had surveyed cross sections, more than 600 surveyed cross sections. We had high resolution LiDAR. We included the hydraulic structures, tidal wetlands. Every single component in this area was included in order to get a representative simulation. And coastal boundary conditions were used here, observed with the observed flow hydrographs from the upland hydrology. We compared with some of the high water marks, which is sort of giving us a good representation. These high water marks were obtained from USGS, and they were deployed prior to Irene and Sandy. We have a good correlation with them, but we want to see what happens if you were in a forecast mode. If Sandy would to happen maybe in a few more days, we wanted to see. And what we did, we used retrospective forecasts. And here you see the storm surge. It's very similar to what we noticed in hydrology. As we get closer to the event, we start seeing that our envelope of uncertainty, and what you see here is the 95th percentile, and expect as much as this. The 5th percentile and the median are showing us sort of how this envelope of uncertainty is starting to reduce with time. And how does this translate on the ground? Because again, our clients, if we just give them this, I was once talking with when we started this project, and I was telling them, oh, it can be this, and there can be this, and he's like, one phone call is going to cost us $50,000 just to move equipment. So you need to give us like more accurate or more information that our facility managers can use. And then we started implementing sort of these spatial maps and these what we call probability of detection criteria and so on. And what you see here is some of the maps we give our clients, which is what we do is we take the 95th percentile. So you're definitely going to get something within this order, because even the 5th percentile in Sandy is showing flooding in some areas. This is the most probable scenario, because this is sort of the post-processing of all the ensembles, and what you see in green is hits. So this is what happened. We're comparing with actual USGS flood extent, and you can expect as much as this. And with Sandy, this is what happened. The 95th percentile is what was representative during Sandy, which was still enveloped within that uncertainty envelope we are producing. And what you see here is the probability of detection, POD, and you see even the 5th percentile is shown 23%, the average conditions, and then the 95th percentile was the representative. So this is the work that we are now in the process of publishing with advances in water resources. I want to show you the website that we finished implementing for Port Authority and New Jersey Transit. So this is just an example. When they start zooming in, they would look at these lines. So major, flood threshold, moderate, minor, and so on. And this is the 5th percentile. And this is Sandy minus 72 hour of the ensembles. And then they want to click on the most probable scenario, then this is what they'll see. And then if they want to click on the potential for this much, and then they can get these scenarios. And here they see the water depth above ground. Okay, and this is what happened in Sandy. So it was again within the 95%. So these are the sort of projects that we're creating, and that are taking into consideration these different components and complexities. At this point, it requires high resolution models. It requires a lot of computational power. But again, as I showed, like a few years ago, it was not possible to maybe run something like WHYDE, but maybe in a few years from now, this can be a project that is available everywhere for people who are in vulnerable areas. To summarize, showed you a multi-scale ensemble-based framework. It's providing accurate results, or good representation of forecasts, at least, if you will. But we show that how the uncertainties can cascade from one component to another. And we saw also the advantage of using ensembles. But again, this ensemble advantage needs a lot of post-processing. So you might be representing the overall flooding, but if you want to look at the peak, right? If you're processing that ensemble in a simplified way, then you might be smoothing your peaks, right? What keeps us up at night is basically trying to understand where to invest more time. Is it, for example, investing more time in the structure of the model? Should we move from a lumped hydrologic or semi-distributed model to a fully distributed model? Should we invest more in the parameters and precedent conditions, like what we saw, how they are important? Or should we invest more in trying to pre-process uncertainty in meteorological inputs, because we saw how the spread is high? So these are some of the scientific or the research questions that we are trying to answer. We have some work on that we're currently trying to also publish. Other components that are very important that we are eager to improve is reservoir operation. So we are working on some dynamic programming and some machine learning on some of the reservoirs in the area, trying to better understand that. Groundwater components, we saw how important that is. And we're trying to see how feedbacks from or two-way coupling with different components can improve our results as well. Because at this point, mainly, you have the hydrologic model feeding freshwater inputs to the coastal model, and then the coastal model feeding back to the hydrologic model. But these are sort of what we're exchanging is boundary conditions. But if it's an iterative process at the same time step, which is maybe important for hydrogeology, then we want to see how that can improve our outputs. With that, I want to thank you very much for listening to my talk.
Any questions?
I have so many questions that I
Well done.
But okay, so I'll try to answer just one. Data simulation.
Yes.
So how do you update your states, especially for your hydrological model, but even for the hydrodynamic model?
So the hydrologic model, what we've implemented, again, you have a infiltration component, right? You want to see how much of that water is going to infiltrate, and then you're going to calculate your precipitation excess. So what we did, we sort of did a dynamic approach that we're still in the process of testing, where we see if you had rainfall for the last 2 weeks or 3 weeks, then how these parameters will start to change. How is my, for example, initial abstraction going to change, or base flow parameters. So these are things that we have sort of lookup tables, and we start looking at, okay, this is what happened, and then maybe this is the set of parameters I should use for this event. And it's this one is not completely out of the loop. At this point, we sort of look and evaluate if there is a given event, but we want to get this one optimized using some techniques such as machine learning to have it outside the loop.
And do you look at the National Weather Service?
Yeah.
Historical forecast?
Yeah, because if you look at our website, you get both. You get AHPS and you get our forecasts. And basically, our forecasts go more. They go 96 hours in the area that we are, and their forecasts go to 60 hours in the future. So sometimes we get very close to each other. Sometimes we predict a peak that they don't have, and so on. But that's something we definitely look at.
For your flood product and your contingency statistics, the USGS map is sort of a binary flood, no flood based on high water marks.
Yes.
Like that. What did you use as your threshold for inundation? any water on the surface from the hydrodynamic model, or was it some minimum depth criteria?
So we had, what we did is we did post-processing on our results, and we came up with maybe, our threshold was approximately 0.3 feet.
Okay.
But we can, that's something actually we want to see, because at the end of the day, you can maybe say, okay, your threshold can be 0.5 feet or 1 feet.
Yeah.
It doesn't matter. You start to worry maybe after having 2 or 3 feet of water, which kind of create more forces on people or move debris. That's where you want to. And we also looked at the uncertainty when within the USGS extent map as well. So we took sort of 10% higher, 10% lower from that total flood extent. That's something we also included in this paper in the process of publishing.
Okay.
Yeah.
So when you first did this, did you choose the threshold in advance, or did you sort of look at it and say, this is the threshold that validates and best with what the USGS?
No, when I first did it, I didn't take that threshold. No. Yeah. And then we started looking at thresholds later.
I mean, it's an interesting way to sort of calibrate with that threshold.
Yes.
Yeah. Like you said, you want to do it based on impacts, or you want to do it based on an actual validation of what some data said.
Right. We had high water marks that we looked at, but the extent of the USGS itself has a lot of uncertainty.
Oh yeah.
Yeah.
And it's interesting because those are, when the USGS does this, is it always flooding from off-channel? Channel processes?
Yeah.
They're not doing any of this.
No. And then we had some areas in our model that was showing miss, not hit. And some of my students and I, we looked at it, and we went to some of the addresses, and we looked on YouTube, and we found that people had water up to here.
Yeah.
And our model was showing that was a miss. And we have these screenshots in the paper to say that these
Show some stuff from the Houston flood. We saw a lot.
Yeah, a lot. You have a lot of uncertainty. Yeah. That's why, I mean, satellite can be of interest, but in this highly urbanized area, you really won't see much.
So, but one of the, this fantastic system, I should say, this is really congratulations. Is also your, if you give us some more hints on the observing system that you have on land, on the urban, that is coupled with your modeling makes it really important.
Yeah.
And so you went, so you put water levels on the lamps, on the street lamps, and then what else? Measure temperature.
So we have in the Hudson we have buoys. We have measured salinity, because the 3D CCOM model does simulate salinity. It does simulate these processes. So we have sensors that measure salinity, that measure water level, and we use these sensors to initialize our models to see how our models are doing every 6 hours. These sensors give us data every 6
But
months.
these are in the Hudson.
These are in the Hudson.
But then how about on land?
On land, we have USGS gauge stations. We are very lucky because the Hudson River Basin is very rich in data. I don't think I can get some similar skill if I'm applying this to somewhere else where you don't have all that.
We should always say that we need all that data.
Yeah, absolutely. It is very important. And even it goes back to what Vincent mentioned. So not only we change the parameters on the fly, we also take the initial conditions from USGS as well. So that accounts sort of for our initial basin from USGS gauge station, in which they keep changing the protocol to download. And that's why I spent hours between the transit times trying to fix this framework. So it's very challenging to get such high resolution at larger scales, or maybe at the scale of the United States or larger scales. But I think it's a process, and we sort of start seeing many models going in that direction.
It's been a great discussion. Maybe with great questions.
Very quick one. Can you give a sense of the relative cost, computational cost of the high resolution versus the benign optimism?
So we have to give in our contract with Port Authority, we have to give them a forecast every 6 hours. Okay, and we have that cluster of 1,300 CPUs. So NIHOBS would take approximately 2.5 hours to run. The hydrological component would take around 3 hours, and then we have 2.5 hours to do the inland local scale hydrodynamic models. And, this is everything is running on the fly. As we speak now, we are producing these maps for them on the fly with this website and with a protocol on the cloud where they can go and look at videos, maps, everything. Every 6 hours they get an updated map.
Just any more questions? Just a quick question. You showed deterministic ensemble. Have you considered non-deterministic ensembles such as ensemble column filters so that you narrow the?
Yeah, that's something we have a postdoc that is working on. Post-processing of these ensemble members. He's using wavelet analysis, for example. But the question always becomes, are we better off doing the pre-processing, downscaling, or are we better off going in the output of your hydrologic model and doing the post-processing?
Both.
That's
The second one.
the second one. I like the second one. I like to make sure.
The second one.
So-
I have experience.
That's what I keep saying, and they say, no, let's do both.
Yeah, but you know, yes,
So-
you also do the post-processing, otherwise it's too long.
Thank you. Thanks. So you want to use this? So next we have Nadia with river flows into the Adriatic.
Thank you. Okay, so this is the thesis of a PhD student that here many people know is Georgia. She's also a co-convener, and she's now very busy on some very important stuff that is giving birth to a boy approximately these days. So she could not be with us, but she will look the video. Okay, so we started a few years ago to thinking of coupling the river flows with regional ocean models. We do forecasting every day, and we know that we're really poor in our regional ocean models that have a very rough representation of river flow. So I can stay here. Yeah, so I will try to give you an overview of some of the open problems, a couple modeling strategy that we decided at a certain point to undertake. Weather, hydro, and estuarine dynamics, WHYDE. So the river discharge, I will show you some applications with the help of Dave on, and not only the guidance, I would say, not only help of Dave that we did for the application of WHYDE in southern Italy. So it is hydro, is water plus hydro plus NOAA MP plus an Estuarine Box model, which I will talk to you about, and then we were trying to see the next step. You know, we cannot change all at once. So we know we have to go with the unstructured grid models up the rivers and so on. But we need also to get better the regional models within where we nest our coastal models. So we take an intermediate step, which is this one. We call it the Estuarine Box model. And we were lucky because NCAR was doing the same step for coarser resolution model. So I will show you the results for this. And then we actually did the coupling of up to the estuary with the regional ocean model. I will show you the impact of the different Estuarine Box models on the shelf dynamics and some conclusions. So this is the estuary, this is the salt water and meeting the river discharge. This is the head of the estuary, and this whole process is affected mainly by tides that not only do bring the water in, but they also mix. And so this whole process is extremely complicated. This is the salt wedge, or the which has so many implications for health of the ecosystem, land and ocean ecosystem. So forecasting regional models at this time at this time are 1 kilometer resolution, but they still don't resolve this kind of area, which is of the order of 100 meters. And so we need something for the estuarine dynamics. So what normally the regional models do is consider this river discharge to go here. And but we know that there is entrainment from this salt water into the surface flow. So the surface flow, if upstream the river is something, it can be much larger downstream. So when it exits. Okay, so this is a first problem. And then also very often we use zero salinity value imposed at the river mouth of the regional ocean models, generating unrealistic gradients, which then will mix depending on the mixing scheme of the regional model. I mean, something that we don't have control. Okay. So just to show you the effects of rivers in the deep ocean salinity, Georgia first paper was about river runoff influences in the central Mediterranean, overturning circulation. So you can see here two very basic runs. This is a root mean square and bias between Argo floats and model simulation in an experiment where the Adriatic rivers are on and the Adriatic rivers are off. And you see, this is 1,000 meter root mean square salinity error, and there is also the bias. And you see that, you know, in the case with rivers, practically root mean square error in the deep ocean is 0, and we have instead much larger. So rivers at the coast are not only affecting the coast, they're affecting the deep ocean. This is part of our thesis, again, the first one. So this is north, south, it's the meridional overturning circulation for the Adriatic Sea. We have a meridional overturning. You see this is shallow area and going deep and deeper in the Ionian Sea. This is the experiment with our runoff, very energetic thermoline overturning circulation, and with sorry, this is no rivers. The realistic rivers is much weaker. If we would have this one, we would be in a different climate. This one. Okay, so this is rivers are important for climate, important for regional forecasting, for everything. So we thought about the coupled water modeling strategy. And so we took WRF system, the WRF hydro system with all the components, and Dave this morning gave an excellent presentation, which I shouldn't repeat. And especially what I would like to show you that we have this 2D overland water flow, which is a shallow water steady state model, which does bring the waters, if they stay at the surface, down toward where the inclination of the land tells them to go, and then it does have a sink due to, has also the source from precipitation, the sink due to infiltration. And this model normally is a 100-meter grid nested into a wharf that is a few kilometers. And then you have the river routing part with the aquifer that we talked about before. And then you have the connection between the river flow and the aquifer. Okay, so what is beautiful of this model is that this is very generic dynamics. Now, it's not generic what is in this IE, because that's very difficult. And And also, part of this one, which is the river routing, is not so generic, but quite generic. So we are getting really close to have the same model. But then we have millions of parameters that we have to define for each area, depending on the land and the subsurface. Okay, so then what we do is we said we take this river flow and we put it at the head of the estuary. We built a estuary box model, which is a two-layer representation, you know, when it's almost correct, even though there are heavily tidally mixed estuaries, so that's failing a little bit. And then we couple this with the regional ocean model. And the regional ocean model uses still a so-called closed boundary condition. It's not laterally open, but it brings the runoff into the vertical velocity, so you get more flow, and the sea surface is higher and is vertical velocity. And that's one. This is so-called natural boundary condition. And then you have this boundary condition on salt, which is needed in order to conserve salinity. Otherwise, you don't conserve salinity. Many models have different approximation of these two. Tom, for many, many years, did not use this one, and still was working rather well. But now is the time that I think ocean models will use at least the salt conserving boundary condition. Okay, so this is our study area. It is, we had the two wharf model domains, practically as, I will get your name. Alfonso, non Salvatore, Alfonso was showing. So the coarser domain order 10 kilometers, and then the 2 kilometers domain in the area of interest. We are interested in this area here, that is Puglia. This is Calabria, you have seen from Alfonso. And so, we specialize also wharf hydro into this catchment, which is a small river, the Ofanto River is called. And here you see, but you know, we focused here because we have data. So because without data, we will not go much far. And then we take whatever comes out from the last forecast of wharf hydro, and we put it in this complex regional model. Okay, so I'll show you one step by step. First, the wharf hydro results. They are published now in that 2017 paper. I will repeat later. So this is Cafiero Station. Cafiero Station is, is probably this one, not the one really at the mouth. And this is the result. So the red is the wharf hydro, the black is the observed flow, and this is precipitation here, the green one. So, okay, we were, well, thanks to, I think, George and David working together, I think we got a good result. And this is from 1/1 to 3/26, so it's 3 months, 2 months and a half time. Okay, so, and we just concatenated wharf, if you want, forecasts. So then, to show you the important, what about the aquifer switched off? Immediately you see that the base flow is much lower, much too low. And so we get bias. You know, this is perfect water flow. And here is when you get only NOAA MP, and this is the one-dimensional modeling. Since I heard something about the one-dimensional modeling, big difference with the one-dimensional modeling. Okay, Okay, so we were quite happy about WHYDE, and we did several other comparisons. So next, we go to the Estuarine Box Modeling, the theory. So we think about an estuary as a two-layer system, and this two-layer system is forced. It is a flat box, and it's a flat surface, and there is a river in one layer, and the other layer is subject to inflow. Okay, so normally you have S equal to 0 here, or you choose to have salinity equal to 0 at the head of the estuary, and then S is greater than 0 here due to the dynamics that occurs in that box. Then in our case, you specify the inflow from the ocean regional model, and you get finally what you need in your regional model, which is the salinity and the water flow. So our Estuarine box model has a two-layer rectangular box. The estuarine, it's a box model, so the governing equations are tidally averaged, laterally averaged, and steady state. And the tidally averaged Estuarine box model is a good compromise. At this point, I will try to show you how. So remember that we have a regional model that has order of 1 kilometer resolution. It's not that we have an unstructured grid. The future will be the unstructured grid. So we developed 3 models because we were curious. The first one is the 1900 Hudson model. So here we see the two-layer flow, the river inflow always in the upper layer, and Hudson is mass conservation and salt conservation. And so I could, if I give as an input this flow, I could get that flow. Why not? So I wanted to try. Then CMCC, we developed a new one where instead we use tidal forcing, and we give still the water inflow at the bottom, and we get again the outflow, but this time we get tidally forced mixing in the estuary. And the other one is Yukon NCAR, and has just been printed, is published, which is used for non-mesoscale models. And in this non-mesoscale model, the big difference is that the inflow cannot come from the coarse resolution model because it's too coarse. It will not have any input velocity in the, so you have to take too large of an average. And so they have 3 equations with 3 unknowns. So have also an unknown, which is the inflow. Okay, so we developed this for our mesoscale regional ocean models. Okay, so governing equation, everybody knows the Knudsen relationship. The Yukon NCAR, 3 equations. We have 3 unknowns. The water inflow on the bottom, the salt in the outflow, the water at the outflow. And given that I know the river in the upstream, and the CMCC EBM, which instead has 2 equations with the mixing, the tidal mixing. And we have only 2 unknowns, the salt in the outflow and the flow and the river flow. Okay, I don't have time to go into this. We can also study these equations in terms of representative processes. We have, for example, these terms are the river freshwater inflow, the ocean water inflow appear in the different equations. The estuarine water outflow in these other terms, the tidal pumping, tidal mixing, and the shear mixing at the interface. Okay, so we do that in the paper. So the first study case is the Ofanto, because we have WHYDE, which has given us the modulated here, estuary head river runoff. So this is the Google map, and you see we've chosen this to be our estuary box model head, and this is the mouth. So our box is exactly in this area, but if we go and classify our Ofanto is a highly stratified estuary, and we have some parameters to fix. So we fixed this parameter on the Google map. Okay, the second case study is much harder because it's one of the biggest rivers in the Mediterranean Sea. It's the Po River. It has a delta, many mouths, very complicated, but we did the Estuarine Box model for this mouth. And we did the same, and this Po delta is partially mixed. Mixing here, the tides do a lot of mixing here. And now at the estuary head, we put observed runoff. We didn't use the forecasted from WHYDE. Okay, so this is the solution. These are the two things, salinity at the mouth and the discharge at the mouth that come out of our box model, given the upstream wharf hydro or observations, as you want. Okay, so this is for Ofanto. We see the three models, Knudsen, CMCC, EBM, Yukon NCAR, and climatology, and so on. So, well, it's not so on, but blue, purple, and red. And you see, let's concentrate on the salinity first. This is the famous 2.5 months. And you see that CMCC, EBM, and Yukon give similar results. But you also see how much the salinity fluctuates. If we want to get the real salinity out of a river, we need that fluctuation. We cannot have, this is our climatological value that we set by knowing the dynamics of the Mediterranean and the Adriatic. I choose 17 PSU. So this is our ad hoc choice that we have done many years ago. And this is what is really, I think, by a good degree of approximation. I don't have data here, but I'll show you the comparison with the data in the next, in the Po. In the Po, I have the river. I have the data to compare. And the discharge. See the discharge, how it varies in this case. And this is a climatological discharge that we put. Okay, so you see now, in this case of the very stratified fluid, the two models give almost the same results. Now here's the difference. Now this is the salinity again, and here you see this is the Yukon NCAR model, and this is our model. We give much higher salinity in the mouth of the Po River. And these are values that are close, as I will show you, to reality. Let me show you now. First, I will, so now I have the box model. I have a river upstream, the box model. Now I couple it with the regional model, okay? So, and I use to couple, this R is the one that comes out of my, here, from my box model, and my salinity at the mouth is the one that comes out of my box model, which has that fluctuation. Okay, so here it is. Okay, now I go first in the easiest place because I don't have the data here. So what I do is I say that I do a NEMO experiment, a regional model which goes inside an estuary. So I say, this is my truth, okay? So let's see. Now, this is the Yukon which has a nice plume. We don't know if it is true or not, but this is the one where if I would use climatologies, as most people do, and this is the one with the CMCC box model. We know they are very similar, so the coastal dynamics is very similar. Oh, let's go instead now in the Po. And in the Po estuary, now we have, this is the salinity plume out of the climatology. This is the Yukon model, and this is the CMCC. Here the salinity starts to be very different between the two models, the Yukon NCAR and the CMCC. And I have now two buoys, the Arpe buoy and the Ismar buoy. These two black dots to compare. Okay, so here it is, the time series. The green is the data. I hope, no, sorry. The black is the data. Okay, we have, starts only here at the data. And you see that the two EBM give the correct salinity. The difference with the climatology, you say, how come that the climatology gives me all that? Because we are already offshore. So these buoys are 5 kilometers or 7 kilometers offshore. So this is what a model would do by giving an ad hoc value of salinity at the river mouth and then mixing with the dynamics of the model, the regional model. But the error here is of the order of 10 PSU. So not a small error. And now if I do a statistics on salinity, the CMCC Estuarine Box model has a root mean square error, which is the lowest. You see the comparison with respect to Yukon and definitely the climatology. The bias also, okay, then the correlation. So we actually improve the regional model salinity by using the EBM. And the same thing is for the Ismar buoy. So same skill, 4 or 5 and so on. Here we have an interesting effect here, which I don't have time to talk about. So the WHYDE approach gives realistic estimates of runoff and river plumes on the shelf. A wider implementation of this box modeling is now ready to go for ocean forecasting at global and regional scales. And we will use the CMCC EBM, and this will be part of the thesis of Damiano that is starting his PhD. So 3 EBMs have been intercompared for different estuaries. CMCC EBM and Yukon give the same results for heavily stratified estuaries, but results differ when the mixing due to tides is important. Weakness of the present approach, the steady tidal yaller dynamics of the EBM, but my prospect is that for the next 5 to 10 years, if we have to concentrate on regional models that are structure grid 1 kilometer size, we need to have that intermediate step. The next step is a better EBM, which we are already thinking of doing, and high resolution and structure hydrodynamic modeling from the coast to upstream river runoff, which I think is the work that also Emil is starting and that other people are also starting nowadays. And this is it. Thank you.
Thank you. Questions, please?
So in these, your river salinity is always set to 0?
Yes, most of these are normally, you mean the forecasting model that we have now, for example, some rivers are set to 0, some others are set to 30. The Rhone River, for example, is set to 30. The Ebro River is set to?
No, the Ebro,
Sorry.
around 125.
So, and everybody has to choose his value. It's totally ad hoc. In global, in the sort of IPCC-like models, very coarse resolution, everything is 0.
How do you define your boundary conditions for them? The fresh water and salt.
Yeah, it's not a boundary condition, it's a surface boundary condition with W. It's not an open boundary. Our Estuarine model gives the runoff that goes into vertical velocity, and it gives the salinity that goes into the salt compensating boundary condition to conserve salt. Okay, so if you open, then you would have to have an open boundary condition. And normally what we do is that we run up to the river runoff where salt is equal to 0. So you start without any problem. And I know you said that your salt becomes very early different from 0, but it becomes 0 at a certain point. Don't worry about it. So at a certain point, the salt is really 0. You can measure where it is, and there you can start to put the runoff coming from wharf hydro, S equal to 0, and then have the ocean model do the rest. So you don't need to do.
So you have, for example, the storm surge coming in. How will that change this one?
Okay, now if you use the future one, it's no problem, right? In our case, it will come through our velocity on the bottom, which is a weak coupling, because we give the coupling to the regional model through the bottom flow. Not a very good, it's not excellent, I would say. So that part is not yet, well, it's not the aim of an Estuarine box model, because my experience in doing this coastal modeling, when you nest into an operational regional model, is that you have to start from better initial conditions. And so now the regional models are really not good. So we are discussing at lunchtime. Either you do some kind of fancy initialization between your coastal model and the regional model, or if you just start from sort of a cold start, it's really a problem if you don't have a better regional model.
Another question.
Yeah, just curiosity. In perspective, I imagine that you need to talk a little bit about this with the map. You need to know all the discharge of all rivers.
Yeah.
This is a very huge work. Did you start to see to any simplification? What kind of approximation can be acceptable?
We are now with wharf hydro. We're not going to leave wharf hydro.
Yeah, but you need to calibrate the file for hundreds of rivers.
Yeah. Well, now Damiano has his first part of this thesis has found 32 rivers that are the most important one. And what is the threshold of? Yeah, so choosing 50 cubic meter per second as the limit, as the threshold for giving important rivers in the Mediterranean. We have 32. We can manage a 32 wharf hydro in each basin. 39, sorry, 39. I think we can. And the Med is a wonderful place to do this example because it's always closed. So.
What river of hydrology do you use?
We use well, why don't you say it?
ERC, which is a German database.
Very good one, I would say, right?
And then we have data sets from Perseus project, which is a project.
Yeah, but that's lousy, unfortunately, because in fact the database goes through the researchers. So if you ask us, we give you. If you're interested in the Med, we have Perseus database, which we can share with you, I say to everybody, for the Med rivers. But I think in Europe we're still scarce on how to share the data sets between projects. And so I would recommend the GRDC, right? The Global Runoff Data Center is called, it's in Germany. And they have long-time series like, I don't know what you think, Emilio. Is a GRDC a good one?
That is no good one.
Okay, no good one, okay. No
That's
good
gonna be
one.
his own, right? He's gonna show.
He's gonna show.
One quick question on it, perhaps bridging to what Emil's going to discuss. Non-hydrostatic terms in your box history, are you considering that?
No, not at all. Our equations are two-layer equations with hydrostatic assumptions for the interface. No, absolutely.
You don't think that's one?
I think if we go with the models, no. I think that the next step will be that there are other things that we need to put in the Estuarine Box model. For example, temperature effects. Not only salt conservation, also temperature, because the river waters come out much colder during the winter than the sea, and they come out much warmer during the transition season, spring. So they're already hot during the spring. So we need to consider the temperature effects, and more or less I think that we need to go to the next step. Yeah, structure grid. Yes.
So, next talk, thank you. Physical processes in straits and estuaries. There's also an unstructured numerical model. There's no change? Okay. Maybe we have to plug in the... So we still have batteries. So this is PowerPoint, Emil?
Yeah. I would just.
But perhaps you can escape and then you start. You want to plug it on no?
Anyway, it's not a big problem. Okay, we start now.
Yes.
So I have one very, very old graph from maybe more than 30, 40 years. And I show this sometimes to my students just to say what is important, what is not important for the ocean. And what you can just compare is the river runoff, which is 10 times smaller than the precipitation and evaporation of the ocean. So if you make a small error for the ocean with the river runoff, it is maybe not so bad. If you make error for the Baltic Sea or for the Black Sea, which are in those bases, where the river runoff is perhaps more than the precipitation or evaporation, then the situation gets not so nice. If you go into the estuaries, it is even worse. So then we have to look for how to prescribe the best possible river runoff data, and maybe we can study something about that by our experience with the final resolving model to see what happens in the estuaries. So I start with two citations. One is for the Baltic Sea, and what you see on this picture are different components of water balance. And what you see is that the water balance is dominated by seasonal change of input and output waters from and to Baltic Sea. And these are very substantial, and the impact of Atlantic salinity or fluxes is comparable or even smaller. So it means that it is very important for the Baltic Sea for the Baltic Sea to prescribe the right river runoffs, and this is also the case for the Black Sea, when we recently did some fine resolution experiments, and we came, now it works. And
You do some
yes,
climatization.
it is too slow to initialize. Sorry. Okay, and now we found something which we knew for a very long time, that you cannot put together kind of what is this?
Firefox.
Firefox is not legally built.
So if you put different types of data together, like monthly, seasonal, or whatever, and if you have only climatological data for river runoff, then you can make big mistakes. So I start maybe from the end of my presentation where I have to justify that it's very important to have fine resolution data. So what you see here on this graph is sea level in the Mediterranean and Marmara Sea from one side, and in the Black Sea and in Azov Sea from the other side. The black points are the Black Sea observations, simulations, and they just show some discrepancies in time if we don't prescribe very correct river runoffs. So the question is how to proceed further. And I think that one good solution is, partially one good solution is to have good models, not only good input data. And our experience now is with this coupled system of Azov, Black Sea, and the Mediterranean Sea, and with the North Sea and Baltic Sea. Recently, we are developing some fine resolution estuarine modeling, which I will also be shortly addressing here. So actually, Nadia gave very nice introduction to what I'm talking about. The story started from Marseille. It continued at the time of Knudsen. Now Nadia gave some further continuation of Knudsen with simplified models. And maybe we can just think of, with the present computational capabilities, to do even finer resolution and process modeling to study the importance of this river runoff. The problem in the past was that unstructured grid models suffered from serious drawbacks. They were not resolving baroclinic instability. And even there are very funny things in the literature you can find as far models with homogeneous water. I don't know this rho equal constant. Yeah, there are publications of it. Shallow water, but in estuaries, you know that salinity changes sometimes. Sometimes it is very important. So, but in most of the unstructured grid models, it was not very easy to tackle with baroclinicity and things like that. And there are recently some models. One of these which we use is the kind of further version of the known self model, where we have the baroclinic instability, we have model polymorphism. You can run the model as 3D, 2D, or 1D even model. And the model is appear to be quite efficient. It is a little bit more expensive than structured grid models. We compared with NEMO, and but we are good with scalability also, so we can pay for this by these good characteristic of the model. So I'll give you some information about what we do with the Baltic Sea. So we force our model with 7-kilometer resolution atmospheric data from Cosmo model, and we take EHAR. So it is controversially whether we have some positive or negative consequences of using this data. For this specific couple of basins, North Sea and Baltic Sea, it appears that the Swedish people did much validation, calibration, etc., etc. So we compared with data from Koblenz, and it appears that this type of data are relatively good. So we proceed with this forcing, run the model for a couple of years, and focused on the processes of the performance of the model in the straits. Baltic Sea is connected to the Atlantic Ocean through 3 straits. This one, Sound, is 4 kilometers wide. This one, Great Belt, is about 15 kilometers wide. This is the Beja Passage. And there is another one which is only 1 kilometer. So in order to resolve all these traits, you need to find resolution, and you see what resolution we have here in the model. In the little belt, we go down to, I think, 80 meters resolution. So challenging was to do some validation. So we take some data stations north and south of Kattegat, and Kattegat is here. And there are these stations north and south of the strait, and there are tidal gauge observations. And interesting is just to see what is the difference between the stations north and south. And then to compare with some old models which have been done or calibrated against ADCP data. So what we see is that our unstructured grid model matches very well the kind of semi-observed data. So this is a parametric model which has been developed on purpose for this area. What is also very nice to see is that we, in a cooperation with Danish people from DMI, we got some data, ADCP new data for the last years. So we compared the exchanges to these two straits, the main straits, the Sound and Great Belt. And although the agreement is not perfect, the qualitative and also the quantitative agreement is very, very good. The correlations are good. We just did some quantified analysis of that. What is also good is that the salinity, which is observed on several stations in the Baltic Sea and in the Straits, the surface and at the bottom matches relatively well the observation. So keep in mind that salinity changes from 10 to 25. So you have huge gradients. You cannot get perfect agreement with the observation because of the big variability. But if you just scale the error with the variability, then the errors are relatively small. And now I will show you something which is interesting. Then we took from operational Baltic Sea model, which is part of Siemens, their output. We compared with our simulations. So, and the results look like that. So our simulations are compared with the observations. They are okay. And so what you see is that the Siemens model is replicating a little bit the truth, but not fully. We focused on some specific events, and this is the situation now. What is on one side, you have our model, and the other side you have Siemens model. So salinity, these are salinity inflows, so there are inflow, outflow in the both directions. So this is Sound, and this is Great Belt, and this is Little Belt. So there are some qualitative similarities, but quantitative, the situation is not good. It is not correct to say that their model is bad. Their model is just not enough. It does not have enough resolution. It has resolution of 1 kilometer, and 1 kilometer resolution you cannot do good work for this area. And what I want to also to show is similar example afterwards for the Black Sea and Marmara Sea and Aegean Sea. Actually, we start from the Sea of Azov, which is the shallowest most basin, sea basin in the world, about 10 meter deep. Then we have Kerch Strait, then we have Bosphorus Strait here. Then we have Dardanelles connecting the Marmara and the Mediterranean. And so we have a resolution of about 70 meters in the Bosphorus Strait, a little bit also in Dardanelles, and a little bit more pores in the Kerch Strait, which is a little bit wider. What is this? So sorry for the typos. I wrote here something for myself just to remember. I forget to remove this. Apologies. So what it is important to know what we have done in the past and what we are doing now. So this means about the earlier problems. So in the past, there were big problems to just get the right sea level in the Black Sea, because if you don't have river runoff correct, then you don't have sea level. So we used to compare the models again, satellite data, altimeter data, and the problems were not so nice. So we developed some methods to remap river precipitation data based on long-term statistics of 40 years on the rivers. So we created synthetic river runoff data based on statistics from the past. So we used the real time precipitation data, and we, in this way, computed statistically the river runoff data. Then, with this river runoff data, we had also satellite data for topography. So we miss one more boundary condition. This is the runoff from the Bosphorus. So then we made kind of best estimate by approximating the Bosphorus transport by constraining the model with the satellite observations. So in this way, we closed the system. The system was good, but it was not perfect because we constrained it by observations. So with this exercise which I am showing you, everything is done automatically. We just use the presentations, the data and the operation as they are, and we just succeeded to very nicely simulate the two-layer exchange. For instance, in the Bosphorus Strait, you see different situations. These are the strait is very strongly stratified. We get low salinity Black Sea water at the surface, and you have high salinity Marmara Sea. And this front goes back and forth depending on the wind. Actually, this is a system which is about 30-meter depth, and it is strongly dominated by frictional currents. And depending on the wind, you get different exchange. So what you see here is the temperature. So this is the non-cold intermediate layer which propagates from the Black Sea, goes on the surface at the top in the Marmara Sea. So this is the back and forth propagation of the salinity front. So what you see here is the turbulent kinetic energy. It is higher at the surface because of the wind, bigger, or on the bottom for when you get inflow events. And this is velocity, which shows you maximum velocity at the surface and at the bottom, but in the opposite direction. So blue is zero velocity. So we compare this model again to observations for a couple of years, which have been carried out for a couple of years, and you see that more or less the model replicates what has been observed. What you also see is that if you plot the transport to the Bosphorus Straits and the wind, you see a very nice correlation. So it is this system is just wind driven. So I think that this is the important message to show, is that all these estuarine processes, this is an estuary, are not only dependent on tides, but are very strongly dependent on wind. And if you don't enough well resolve the wind, if you have coarse resolution data, or if you have bad sampling in time of the wind, then maybe you can make big errors. What you see here is that the mean vertical stratification shear of velocity matches the observation. So this green is correspond to this one, but the variability is too big. You have this two-layer transport about which Nadia was talking. So you have surface current in one direction, bottom current in the other, and they go against one each other. So this is a process which really needs much of effort to be correctly parameterized. So I just give you my third example, which is with our finest models, which we run now. And we have three estuaries. So these are very nice couple of estuaries. one is very big, Elbe River estuary, and then this is weather, which is some time in between, and this one is between 40 and 200 cubic meter per second. So Elbe is one of the biggest estuary in Europe. So if you run the model for a couple of months, you get the statistical steady-state situation. So you see here, actually, I show low water situation in order not to have it simpler. You have salty water in the ocean, you have very fresh water in the rivers. So this is actually the area where is the mouth, where you really need to know what happens. This is a very dynamic area. So this is the front area of the Elbe River, this is the front area of Weser, and this is the front of Ems, which is small river, is put very far behind the barrier islands. So the problem is in the tidal dynamics, in the estuarine dynamics, that you have two forces. From one side are the tides, and from the other side is the river runoff. Based on their competition, we have either pushing the estuary in the open toward the open sea or back. But on top of that, there are wind waves, etc., which can change the situation very dramatically. Another interesting issue is in this area which I show you, most of the processes are dominated by M2 tide. So this is a simple result of tidal analysis. So you see that the larger tides are in the coastal area. But what is also important is that when you go close to the coast, then you have relative increase of M4 tide. So you see how low M4 is just nonlinear deformation of the tidal signal. So there are some areas of refraction and reflection here in this area. And when you go into the estuaries, then you see the large numbers of M4. So M4 in the estuary start to compete with M2. So you change the asymmetry of the tidal signal, which makes the dynamics very complex. So I show you, but there is another level of complexity, and this level of complexity is associated with spring to nip variability. So we have sampled this part of the signal as a spring one, and this as a nip one. Just keep in mind that you have these blue lines, which are the model results, and these purple ones are the result of tidal analysis. So you analyze the signal with tidal analysis, and you don't get enough information for some specific periods which are dominated by strong winds. We don't have enough good representation of the circulation in this area. What you see here on this graph is the mean, the mean situation, the spring mean situation, and the difference. So the difference shows big numbers. The changes are comparable to the salinity. So, and these are 2 weeks periodicity where you have a strong coupling between atmospheric variability, synoptical signal or cycle, and nip and spring variability. So it is not very easy to get all these things with the simplified model. Of course, I do very much simplified model because they give us good tools to understand the situation. But unfortunately or fortunately, the real situation is very complex. And for some specific reasons, we have also to consider this type of variability. Important for these estuaries is also the issue about the sediment transport. What you see here is the change, the salinity front, so the decrease of salinity. These are observations. And when the salinity drops below a certain level, then starts to appear estuarine turbidity maximum. And this turbidity maximum is very strongly dominated by the turbulent kinetic energy, as you see on this figure. So I have here one. So what is this? This is the SPM concentration for one specific green from one specific size of sediment, and then I have a long channel velocity, and I have here the turbulent kinetic energy. So there is constant change of the dynamics, and this dynamics appears in this curved region. Oh, I'm sorry. Something has because this is so moving. I wanted to just show you how this looks like. So this is El Primer estuary. This is the bifurcation. This is the bifurcation here. And now I don't show you only low water, but I'll show you all. So all this salinity plume goes back and forth. So these are the vertical sections of salinity loop in one direction, and this is in the other direction. This is the secondary circulation. And this is also very important. For the estuaries, it is not only important what goes back and forth, but it is also very important how the helical structure of the circulation looks like. And depending on this helical structure, you have a kind of modification of the position of salinity front. So the basic physics of the estuaries is not only the fact that we have a long channel gradient of density, but we have also gradients in the cross-channel direction, which are mostly due to either Coriolis force or to the curvature of the estuary. So also the curvature of estuaries have to be represented, and as you see here, the estuarine front or salinity front is entrapped by the curvature of the river estuary. And this is another thing which we have to keep in consideration for our future studies. So because this movie is very big,
Maybe you probably have to turn it there. No, you have to push it and you look at the computer. No.
And now I just want to illustrate one agreement between observations and simulation. We have in our institute some system which is called ferry box. So between Cuxhaven and UK, there are regular ship cruises on covering this distance once per 3 days or something like that. So and we just took from the observations this part of their transit, the trajectory, and we plotted the observations, and we simulated for the same time when this observation had been done. And you see that it is not absolutely perfect, but the agreement with the observations are not kind of disappointing. There is a good qualitative, at least, agreement. So I think that this estuary model can be used for practical purposes, as we recently were asked by German authorities who are digging with which are dealing with digging Hamburg port. Actually, the problem there is that they want to bring bigger ships to Hamburg, and if they dig, then they change the tidal propagation signal. And if it happens, then it changes the sedimentation, etc. in this area. So they want to just have some estimate about possible response of the river to either climate change or to human activities. I will end with the finest most simulations which we did, and this is with the smallest estuary. Just to give you some information about how important could be the change of river runoff. So we just did two simulations, one with 40 cubic kilometer per second, and the other with 140. So we sampled two different situations of river runoff. So for these cases, and I show you the difference. So this is how different can the position of salinity form be. And you see that here is the difference between spring and nip situation. So these are also comparable. So when you just simulate the response of estuary, so when you just want to give a boundary condition for the ocean models, also spring nip variability, but it has to be considered because it is comparable to the variability which is due to the biggest or largest river runoffs. I will end my talk with showing this picture for the Baltic Straits. You see, it is a big difference between salinity. You have Baltic Sea with salinity of about 10 at the surface, and you have Kattegat with salinity of about 30 at the surface. So these estuarine processes are, in my opinion, very difficult to simulate. I don't think that the model is kind of which we are running is a perfect solution of that, but I think that it gives one kind of perspective to further credibility of what we are doing. And the validation was, in my opinion, motivating for using this model for further physical analysis. And to understand, because we use the model as a tool to understand the physics of an estuary. There are not enough measurements, so if you just think that the model can replicate the nature, then you can analyze model data and learn something further about the estuaries. So finally, I want just to again mention that we have to further increase our efforts toward the coupling of oceanography and hydrology, and I am very glad that we have taken this initiative and bring these people here to consider these issues. Thank you.
Thank you. Any questions?
So, how far in the Elbe River do you go upstream, and who gives you the river runoff from there?
Elbe River, a kilometer, about 100 from Hamburg, or not, maybe 50 from Hamburg and 100 from the mouth, is not anymore normal river. There is a barrage,
There's a dam.
Dam.
Okay.
So just water jumps from one level to another, and it is almost never happening that the river propagates, the signal propagates any further.
So it is regulated.
It is regulated. In cases of extreme flood, it could happen. The ocean signal propagates further.
So you get the
this
data.
has not happened in the last 50 years since this dam has been built.
Okay, so you get the data from the
So there are some authorities which provide the data for AIMS and for other for German rivers. As far as the Baltic rivers are concerned, we take them from IGA. We compare these data with the ones which are provided by Koblenz, and they are very consistent. Actually, they are based, IGA data are also based on come from Koblenz. And all German rivers are dammed.
Oh, good.
Yeah,
Easy.
And,
You don't think about hydro.
And in Ems, there are actually even storm damage, because they have a dam further into the river, but close to the sea, they have a storm baggage and they can close it or open. And there is another very interesting story with this river, but this is not the place here to talk about that. They deepened it because they built in Papenburg big ships for just touristic ships. And in order to bring them to the ocean, they need deep water.
Yeah.
So they close with these storm barrages the river for a couple of days. Water gets high, and then the ship moves into the ocean.
Yeah, that would be.
The problem is that
That's the old way.
the problem is that they also additionally dig the river. So they deepened it.
Yeah.
Because they deepened it, they resulted in maybe 2 times increasing the tidal range. And because of the increasing tidal range, then the sedimentation changed. And the big problem for this river is the so-called fluid mud. We have very high level of energy of the tide, which erodes huge amount of sediment, which collapses at the bottom and creates something which is something between solid matter and sediment. And it solidifies during part of the tidal signal. So I was talking about with people who are navigating or operating the navigator, they sometimes cannot measure the real depth because of this.
So I have a question. So where should we go as far as estuarine modeling is concerned? I mean, I guess I gather that unstructured grids are useful for very irregular coastlines with very islands and with very irregular topography. But as far as the physics is concerned, do we need better boundary conditions on the landward side? Do we need more accurate forcings in our ocean boundary condition too? Because, for instance, the question I was asking Nadia, non-hydrostatic terms. Do we need more to understand better the turbulence happening on the vertical inside these estuaries? Where do you think we should go into? What is missing?
Yeah, as far as non-hydrostatic is concerned, I cannot much comment on that because I don't have my personal experience.
Sure.
I have read what
but do you think
that's
an important?
Yeah, it would be important if you have strong vertical velocity, then it would be important. For instance, for this fluid mud problematics, this is like a
Helmets.
instability. So you need for this non-hydrostatic. But to another part of your question, I would say that these fine structured models, they cannot be run for the entire ocean. So there was one good example of how a Belgian institute happened. They developed their model for the global ocean. They decided to go in the coastal ocean and to refine the model. And at some point, they understood that it cannot go without nesting. So they started to work on coastal implementation of their global model. So when we talk about nesting, then we have to ask how to nest. I think that very important is to develop interfaces which bring together structured grid models, regional or whatever bigger area models with this estuarine or coastal model. So this is, in my opinion, something which really deserves some efforts. The flexibility of the interfaces which connect the coastal models and with the focus on the two-way interactions, because there are many coastal specific problems which are propagated to the bigger models. So with one-way nesting, we cannot
So, I mean, this is a problem. In fact, maybe in the future we will have global unstructured grid models, and they will all go up to Wharf Hydro River runoff, and then we'll have everything. But, now this kind of modeling should take the place of the box model, let's say.
Sure.
So it goes from where you have the river runoff to an open boundary. And now, for the open boundary, I think we are all set. So it is different. But
You mean an open boundary where paraconicity is?
no, but the problem is, this is primitive equation, it's an outward close problem. If you have open boundaries, the errors will propagate in, so, but, we can, I think this is, okay. My question to you is, the point of the, what is that makes it so difficult, these models to be adapted to each situation? It is the gradient between the coarse resolution and the high resolution near the coast. What do you use as a parameter to decide how to go from coarse resolution unstructured gradient to high resolution unstructured gradient?
So, one very big problem is just to allow to resolve the important processes. I can give you one example. For instance, if you just, I also say this as a bad example which I had, but sometimes one is wrong with the formulation of what is doing. I decided I was very motivated for 2 years to develop a Black Sea model, which can resolve very nicely the continental slope. So this sea is very well known with the sharp continental slope. The depth changes in about 20-40 kilometers from 20 meters down to 2,000. It's like wall. This wall is characterized by many canyons. So I wanted, as soon as I started to work with this model, I said, okay, this is the best application for the model. I will make a refinement on the continental slope to resolve the barophonic instability. So I did this refinement, and I was totally disappointed because if you just change the grid size there, you kill the waves. Yeah. If you want to have a decent parameterization of barophonic waves, you are not supposed to change the grid resolution. So what we are doing now for the Black Sea, we said, okay, use homogeneous resolution, 3 kilometers everywhere, and then think where to couple. So the place to couple, in my opinion, the best place to couple is where you have a friction-dominated dynamics. So don't couple in the areas of strong barophonicity. Then you get problems. So what we do is just we couple on the shelf. There you make some mistakes, but the forcing is so strong that these mistakes are not so bad. So the question is always about the price to pay for what you pay. We did another experiment. We were doing some work with, so this is about what we heard today about these Karman areas. With Karman areas. So depending on the grid size, or the change of grid size, you either can have in the model Karman eddies or not. So after some coarsening of the grid, instead of Karman eddies, you get just waves, but not any more Karman eddies. So it is the problem what you want to keep in the model. So the finite elements models are not solutions for everything. Not to say that sometimes generating grids is to a larger extent subjective.
Artistic.
Yeah, you spend a long time, you focus on some small channel, you want this channel to be nicely represented, but you forget about other things. So it is another big problem of unstructured grid models. So you cannot have this unified presentation as you have in structured grid models for all processes. So these models have to be used for specific purposes which cannot be addressed by structured grid models. And if you can allow using structure, that there is structure, but if you want to go into the rest, it's difficult. Now,
you have another?
Oh, just a comment. This is music to my ears. You have it in writing. It's very important, what you just said. So the experiments you will be described with regular grids versus unregular grids. You have that. Did you publish anything?
on the comparison yes. between structured and unstructured grids.
Yes.
So we have done partially this, and what we have published was on the performance of the model for replicating tidal processes for the North Sea. So we run 5 or 4 structured grid models, and we took another 2 which were operational structured models, and we compared them with the unstructured grid model which we have used, but it was not complete validation. We didn't do, for instance, deep analysis on the dynamics of Norwegian Trench, for instance, which is very interesting to be done.
More questions? So thank you very much.
Thank you.
Thank you again. So this was the last talk of the day, since we all took longer than expected, most of us.
We're gonna postpone the photo to tomorrow.
Tomorrow.
When more of us are here. And meet for dinner.
Yeah, meet for dinner at 19:45 at the Orchid. Oh, sorry, 18:45.
Okay, good.
Just
But
as
just a moment.
you want out
We
6.
want to come to the dinner. so-
Yes. It's paid for, so it's 6:45. Yeah, 6:45.
The presentation.
Yeah.
I don't know.
So he transformed the code into an MCA, etc. So that might be smart.
Something which we also
we had them here.
Oh, really? How is he? He's a very old guy.
See you next never had it. So
Actually, I have 9 hours. The bachelor's, 3 hours in masters.
That's amazing. Wow.
I feel like
No,
teacher in a grammar school.
If it is, no, I would resign. Research work and foundational work is done.
I have around students and they present their thesis in the bachelor, especially in math. I'm reading here and there.
Now, fortunately, I have this PDF ready to sign that I can use.
So it's one of the issues with diecast is you just test fertilize API to make it.
I thought I was gonna die because, because being away and then
was invited by him for maybe 10 years.
Now
This others that you have.
He came from South
and then we went into the problem.
Yes. And you have students.
Students, so that's
So you see, it was also different because I had a postdoc that was using different. The modifier. And it's interesting to see you being the fight with David. The son, the father fight with some
but they are also clever.
Yeah,
In a different way.
Yeah.
They is more sharp.
Yeah. The problem with the original diecast is ad hoc adjustments that you need to do at different time frames in order for it to continue to work. And only they can do that. Oh, but why did it blow up? Oh, because it is a little bit.
I asked him during one IAPSO meeting in Melbourne.
Yeah.
And he was talking about simulating Australian.
Oh, yeah.
And I told him,
Ballman is also his friend.
yeah, both of them are good friends of mine.
Yeah.
So, I thought, why don't you then try to do this for the next series?
Yeah.
And he didn't approach me. So he was somewhere. I got the email. Whether I like this situation. So it was he says that XCCD he was 30 or something. And I understood that he just